this lecture, I'm going to explain to you an application of mobius inversion on the lattice of set partitions to the problem of counting connected structures. So let's let Mn be the number of uh, graphs with vertex set 1 to n. So by graphs, I mean undirected, simple graphs without any loops. So for any pair of elements from 1 to n, I have a choice. I can either connect them with an edge or I do not connect them with an edge. This Mn is clearly equal to 2 to the power n choose 2. Now that was easy, but it's not so obvious if I ask you what is the number of connected graphs with vertices n. So one way to solve this problem is to take a graph with vertices n and enumerate the number of graphs with vertices n in terms of connected graphs with vertices n. So what you do is you notice that every graph is uniquely a disjoint union of its connected components. So what we have is graphs on n, by which I mean graph structures on n. This is in bijection with, well, firstly you take a partition of n, a set partition, and then you put a connected graph structure on each block of the partition. And this is a bijection. If you take your set and partition it somehow and put a connected graph structure on each block, then you would get a graph on the set 1 to n. And so what we get is that Mn is equal to the sum over all partitions of n, set partitions of n, and then I need to take a product over on each block. I can independently put a connected graph structure. So I'll say B belongs to X. Here B belongs to X means B is a block of X. And so you go over all the blocks of X and look at connected graphs on the set, on the elements in the block. And that only depends, of course, on the size of the block. So that's C of cardinality of the block P. Now this looks like a convolution in the set of set partitions on n. So to make it even clearer, let's do the following thing. For every x in pi n, you define firstly Cx is just going to be the product over the blocks of X of Cb, and Mx we'll define to be again the same thing, product over blocks of X Mb. This doesn't have as nice an interpretation as this. These are graphs whose connected components are given by the set partition X. But nevertheless, these two are related by the following relation. M of X is equal to the sum over all y refining X, which means y is less than or equal to X in pi n, Cy. And the proof of this is quite easy. I mean, the statement is pretty much obvious, because if I take M of X, then this is product over B M of size of P. These are graph structures on the blocks of X. So here this is product over B belong to X. And so that's product over B belongs to X. And for each block, I can write this as UB in a set partition of that block. and then I take the product of connected components over that. So this will be just C of UB. Maybe I should write it like this, C of UB. And that is nothing but the sum over. So if you look at this UB, this is a set partition of the block of B. So if you put together the blocks of UB together across all the blocks of X, then you will get a set partition of X, which is a refinement of X. So I'll get Y less than or equal to X, CY. And that proves the lemma. And so an immediate consequence using mobius inversion is that C of X is equal to summation Y less than or equal to X. Then I take the mobius function on pi n of Y comma X my. And so I can express the number Cx in terms of the numbers my, and from this I can extract the elements, the sequence Cn from the sequence Mn. So let me just write down the final formula for you. So we have, maybe I'll write it as a theorem, Cn, the number of connected graph structures on the vertex at n. Well, that's C of the trivial partition in pi n. And by this formula here, this is sum over y in pi n, everything is less than or equal to 1, mu pi n y comma 1 hat pi n, and then we'll have m of y. And I can write this further as, so if you look at the interval y to 1 hat comma pi n, it only depends on the number of blocks of y. And so if I denote by this the number of blocks of y, then this is summation y belongs to pi n, and this mobius function is going to be minus 1 raised to the number of blocks of y minus 1, number of blocks of y minus 1 factorial, as we saw in the last lecture, m of y. So for example, we can calculate C3. C3, well, let's just recall what pi 3 looks like. Pi 3 just has 5 points, 1, 2, 3, the trivial partition, then we have the partitions with 2 parts, and then at the bottom we have the discrete partition 1, 2, 3. And so if you just use this, you see that C3 is going to have 5 terms, 3 of which look the same. And so you'll get C3 is M3 minus 3 M2 M1 plus 2 M1 cubed. And that's just 8 minus 3 into 2 into 1 plus 2 into 1. And that is equal to 4. And indeed, there are 4 connected graphs with 3 vertices, namely the complete graph. And then there are 3 graphs which have, which are sort of linear graphs, depending on which vertex you choose to set missing.